Section 7 of Chapter 1 is about functions. So by the end of this lesson, you should be able to determine whether a relation is a function and then find function values. So a function is a relation between input and output. In a function, there's exactly one output for each input. So let's say I plugged in, let's say I plugged in the number 1 and I got out 2. So plugged in 1, got out 2. And then I plugged in 2 and I got out 3. And then I plugged in 3 and I got out 4. And then plugged in 4 and I got out 5. Chances are, you guys are guessing the pattern here, that whatever number I plug in, I just have to add 1 to it, and that's what I get out. Now let's say I do another one where I plug in 1 and I get out 0. And I plug in 2, what's going on? And I get out 0. And I plug in 3 and I get out 0. And we can keep on going all day. Whatever I plug in, I get out 0. Go back to our properties. This would be 0 times x. I get the same thing every time. So for each one of these, there's only one output for each input. Sometimes it's exactly the same output for every input, but there's only one. So let's say I plug in 1 again, and I get out 2. And then I plug in 2, and I get out 6. And then I plug in 2, and I get out 7. Something like this is not a function because I plugged 2 in and I got out 2 different answers. So we don't know what this is because it's not a function. There has to be one output for each input. And for this, I put in 2 and I got out 2 different numbers. You can't have out 6 and 7. So you'll have some problems like this where you have to determine if the relation is a function. And what you're looking for is if I plug something in, do I get only one thing out? So if we look at our domain and range here, if I plug in -2, I just get out 3. If I plug in 0, I just get out 6. If I plug in 3, I just get out 6. If I plug in 4, I just get out 9. Now one thing that messes people up is the fact that this 6 is here twice. But it doesn't matter that 2 different things go to the same number. Another easy way to remember this is think of this as pizzas and this as houses. You can have 2 pizzas go to the same house. That's totally okay. This is a function. We have one output for each input. And the next one, if we put this in a map so that we can compare them, my domain was 1, 3, and 5. My range is 4 to -4, 2, and 4. And when we map this, 1 goes to 4, 3 goes to 2, 5 goes to 4, and then 1 goes to -4. This here doesn't work. Think again, pizzas and houses. This is saying that this pizza needs to go to house -4 and house +4. It doesn't work. So this is not a function. We can say 1 goes to 4 and -4. It's not allowed. Now if this wasn't here, this would be totally allowed because even though both 1 and 5 go to 4, that's just like 2 pizzas getting delivered to the same house. That's allowed. And the next one is in a point form. Basically, what you're looking for here is repeated x's. So take a look at your x's, 2, 3, 3, and 2. Now, if you have repeated x's, like these two here, that's saying that you plugged the same thing in, so I input 2, and I got out two different things. I got out 1 and negative 2, and that can't happen. And then with the other ones, I input 3, and I got out negative 2 and 1. And again, that can't happen. You can't get two things out. So this is also not a function. So another way that we can identify functions is if they are in a graph, we can use something called the vertical line test. Now remember, vertical lines go up and down. So if a vertical line intersects the graph more than once, then the graph is not a function. So you can drag your pencil across this, but because you guys can't see that, pretend that we have vertical lines all on my graph here. These vertical lines cross this graph once. Every single line only crosses once, so this is a function. Where like this one here, this vertical line crosses this twice, it's not a function. Remember that we said that x is our input and y is our output? What this graph is showing is that if I plug in whatever this x value is, I get out this y value and this y value, and that can't happen. We can't get the same thing out. So the vertical line test is just showing us that you get two things out. Now this next one's a little funky looking, but if we draw vertical lines all the way across, it only crosses this graph once. Now what's really weird is this right here has a closed circle and then an open circle. This open circle represents that your graph isn't right there, but it gets insanely close to that line. So even when we draw this vertical line, it doesn't cross here. It only crosses here. So let's talk about something called continuous graphs and discrete graphs. So a graph that consists of points that are not connected is discrete. A function graphed with a line or a smooth curve is continuous. So let's say we have a bird feeder that will hold up to 3 quarts of seed. The feeder weighs 2.3 pounds when empty and 13.4 pounds when full. Make a table that shows the bird feeder with 0, 1, 2, and 3 quarts of seed in it, weighing those amounts of pounds. So we have our XY table, and we have quarts on one side. That's our independent variable, that's what we're changing. And then we have weight. So if I have 0, 1, 2, or 3 quarts, it tells us that it weighs 2.3 pounds, 6 pounds, 9.7 pounds, and 13.4 pounds. The domain and range will be nice since we set up our little function. Domain is 0, 1, 2, and 3. Those are the pounds that I'm putting in, or the quarts that I'm putting in. And the range is the weight that I get out, which is 2.3, 6, 9.7, and 13.4. Write the set of data as an ordered pair and then graph it. So my ordered pairs are 0, 2.3, 1, 6, 2, 9.7, and 3, 13.4. And we'll draw a rough graph here. 1, 2, 3. We'll say 5, 10, 15. So my first point is at 0, 2.3. My next one's at 1, 6. Then I have 2 and 9.7. And finally 3 and 13.4. So state whether the function is discrete or continuous. So even though they gave us only these points here, stop and think about the story. Would it make sense for me to connect these dots? Would it make sense to have a data point that's in between these two things here. So when you stop and think about that, remember this was quarts and this was weight. If your birds only eat a little bit, it is totally possible for you to have like 1.5 quarts in here and then figure out that it'd be 7.8-ish pounds. So for this, it is continuous. Even though the points don't show us that it's continuous, you have to stop and think about the situation. So we can say it's possible to have uneven amounts in the bird feeder. Now, if I gave you this story, but instead of quarts here, it was like the number of birds on here, then it would be discrete, because you can't have like 1.5 birds. So stop and think about your story before you mark it continuous or discrete. All right, function values was the second part of your objectives. So function notation should look familiar to you. We usually, up until this point, use equations like y equals 3x minus 8. Function notation looks a little different. It replaces the y. Y is going to be the same thing as f of x. So when you read this, you need to say f of x. It is not f times x. And what this is showing is you'll be able to notice your input and your output. So if I give you something like this, f of x equals 3x minus 8, and I tell you that f is 5, or that x is 5, you can plug this in and then plug in the 5 here. Now the point of having this is so that you know the input, and when you simplify this, this will be your output. So you get the domain and range all in one nice little equation. So let's do some. Here's your function. F of x equals 2x minus 3. Now if I ask you for f of 1, that means anywhere you see x, you're going to plug in 1, and then simplify. So 2 times 1 is 2. If I subtract 3, I get negative 1. So your answer is f of 1 equals negative 1. Now I know it's very tempting here to think that those two are multiplication and divide, but what this is saying is that I plugged in 1 and got out negative 1. And the awesome thing about this is if you leave something in function notation like this, you can make an ordered pair of it. You could put it in a table. You could make a mapping diagram of it. It's really useful to know what you got. Where if this was y, we would just end up with y equals negative 1, and we wouldn't know what we plugged in to get that. So let's do a little harder one, like this over here. So it says that we're going to take 6 and subtract f of 5. So we have 6 minus our function, which is 2, and then instead of x, I'm going to put a 5 in there. And then this turns into some of the other problems we've been doing where we got to follow PEMDAS. So we got to do what's inside of parentheses first. If I do 6 minus 7, I end up with negative 1. So 6 minus f of 5 equals negative 1. I'm leaving these two for you to do. Now let's try the next one. F of t equals 2t cubed. So when I plug this in, I have f of 4, which is 2 times 4 cubed. So Jem just tells us we got to do our exponents first, so make sure you do 4 times 4 is 16. Multiply by 4 again, you get 64. And then if we multiply that by 2, we get 128. Let's try this next one. So these brackets are telling us that we need to multiply. So our function It just is f of t, so we're going to leave the t in there because we don't know what it is. And then we got to distribute. So you get 6t cubed plus 2. And we can't combine those two things because one is a t cubed and one doesn't. They're not like terms. So try these two on your own. So determine whether these things are functions. You got 1, 2, 3, 4, and 5. And then for can you find the function values, go back to the last slide and do those ones. Make sure you write down any questions you have and we can go over them in class together. Enjoy your night.